Okay, so I'm going to go back over this because I didn't record it at the beginning when I started talking about this subject. So I'm going to go ahead and record this now, right? So now that we know about our standard reduction potentials, right? So our standard list of our beautiful little electropotentials, or again, I call these guys reduction potentials. And I can't seem to break that, so I probably won't ever. How are we going to utilize these? Well, sometimes they don't actually want you, again, to calculate the cell potential, right? Instead, they want you to just predict based on the overall reduction potentials of something, whether or not a process is going to occur, right? So for example, let's say that we had zinc. This was the example I used in class. Zinc solid plus copper 2 plus. Going to make copper solid, so copper is getting reduced here, and zinc goes to 2 plus is being oxidized, right? So overall in this reaction, we have zinc being oxidized and copper being reduced, right? And if we wanted to determine whether or not this reaction was going to be spontaneous, meaning whether or not this cell potential was going to be positive, we don't necessarily have to go through and calculate it. We can just look at the positions of the two in the table, right? So if we go back to our table, I told you when I introduced this table that everything with these positive reduction potentials, so these guys are all very positive, and up top for this table, all of these guys love to be reduced. And then for this guy down here, everything with negative reduction potentials, these guys tend to like to be oxidized. Right, so to be oxidized. All right, so what does that mean? So in general, what we're going to find is anytime we take something that loves to be reduced and we couple it with something that loves to be oxidized, that's going to generate an overall spontaneous process. What does that mean in terms of just predicting? Usually what we're going to find is the thing that is reduced is going to be above, so reduced should be above the thing that is oxidized, right? So in this problem, we have copper, and when I'm talking about thing or whatever, I'm talking about the reduction potential. So the reduction potential of the reduced species needs to be above the reduction potential of whatever's being oxidized in the process. So in this problem, we've got copper being reduced, zinc being oxidized. If we go to our standard reduction potentials and we highlight copper and zinc, we'll find that copper, which is again being reduced in this process, is up here, and zinc is down here, right? So again, right now, we've got copper above zinc, right? So it's above zinc. It's being reduced in this process, so this would be spontaneous overall. And we could just predict that based on the potential or based on the position in this table because it lists it in order of decreasing reduction potential. But even if they just gave you values, if the thing that is reduced has the thing that is reduced has a greater reduction potential than the thing that is oxidized, then that will lead to a spontaneous process. So who cares? The potential for zinc, if we look in the table, is about a minus 0.76, right? Whereas the potential for nickel is minus 0.23. So if we're ordering these in order of increasing reduction potential, going from more negative to more positive, does nickel lie above zinc? Yes, right? So because of that, the thing that is being reduced, which is nickel, is above zinc. So this is a spontaneous process. On the other hand, iron in reaction B, what's happening to iron? Is it being oxidized or reduced? It's being oxidized, right? It's going to iron 2 plus. Magnesium is what is being reduced here. So the reduction potential of magnesium is a minus 2.37. It's way down there on the table. Whereas for iron, it's a minus 0.45. So the thing that's being reduced, which is magnesium, does it lie above iron on that table? No. So because of that, this is non-spontaneous. It would give you an overall E that is negative, okay? So negative E's are non-spontaneous processes. Okay, so a couple more things before we finish up here. I'm going to skip some stuff because it's not necessary for your doing well on the. Okay, so go ahead and try this one. I skipped this in class, but if you want to go ahead and give this a shot. So in this problem, what they're looking for is something that can selectively oxidize iodide, right? So what they're looking for is the oxidation of iodide. This would be given by 2I minus going to I2 plus 2 electrons versus the oxidation of Br minus. Same thing, oxidation of bromine leads to bromine 2 plus 2 electrons. So what they're looking for is something that would selectively oxidize this, right? So if it's selectively oxidized, it would be reduced. So we're looking for something that would be reduced if it reacted with iodide, right? But would not if it reacted with bromine. And again, this is just going to be based on the position in that table, in that standard reduction potential table, right? So this thing that you're looking for wants to be reduced, and it's going to be capable of being reduced if it's in the presence of iodide, but not if it's in the presence of bromine. So go ahead and look at the table, try to figure out what this is. You have 4 choices over here, and then you can pause it and come back to get the answer. Okay, so the answer for this, again, we're looking for something that will be able or produce a spontaneous reaction. It's going to be reduced. So it needs to lie above the iodide couple, right? So what we're looking at is something that lies above this reaction in that table. So it lies above it, but it lies below the bromine reaction, right? Because it's not going to react with bromine. So if we find in the table, we'll find bromine. Bromine lies above iodide, right? And what we're looking for is something that lies in between these two, right? Because if it lies in between these two, if it's above iodide, it would be able to, again, be reduced, selectively oxidize iodide. But if it's below bromine, it won't be able to do that reaction with bromine. If it lied above both of them, then both of them would be oxidized, which is not what we're looking for. So again, we're looking for something that lies in between them. And the only redox process or couple that lies in between them is this guy, our nitric acid. And the actual redox couple that we are looking at there is, where is iodide? Iodide, we go up, is this guy. It's nitrate, NO3 minus, plus, we've seen this already, nitrate plus 4 electrons, or 4 protons plus 3 electrons, goes to make NO and 2 waters. NO gas plus 2 H2O, right? This is what we mean. This is nitric acid, right? It's nitrate floating around. We know nitric acid is a nice, strong acid. It completely dissociates, so we get protons and nitrate. If those were there, if nitric acid was there, it would be able to oxidize iodide, producing iodine. And again, it's because it lies in between these two in the overall standard reduction potential table. Okay, so kind of a little spin-off of what we've been talking about with respect to predicting spontaneous redox processes, just based on the half reactions and their position in that reduction potential table. Another like spin-off of that is whether or not metals will necessarily dissolve in acids or not. So back in like 151, when we first introduced you to metals, we specifically said that metals, most of them at least, had a tendency to dissolve when you put them in acid. And the actual reaction that's taking place there is a redox reaction. So for example, let's say that our metal was solid zinc, right? Solid zinc, when you put it into an acidic solution, it does appear to dissolve, right? But what's really happening is that it's being oxidized. It's giving up its electrons to protons that are in solution. It's forming its ion, right? So zinc 2+ in this case. And it's also forming hydrogen gas, right? So the overall reduction process is we have oxidation of zinc to zinc 2+, and then we have reduction of protons to hydrogen gas. Now, whether or not this reaction will occur, whether or not a metal will dissolve in acid, essentially can be answered by those positions in that electrode reduction, that standard reduction potential table, right? So if you guys remember, I don't have the chart, which is kind of a hassle here, but right at our 0 volts is our standard hydrogen electrode. That is this reaction, the reduction of hydrogen gas by the reduction of protons, by 2 electrons to form hydrogen gas. Again, any metal that lies below this in the table will be oxidized, right? Protons will be reduced, the metal will be oxidized, and that'll be a spontaneous process. There are a few metals, though, that lie above this, okay? And they're kind of more of the obvious ones. So, for example, copper is above this, right? So copper solid is above this. Another common one, or another one that's above this, is silver. Let me write this: 1 electron, silver to silver solid. And then another one is obviously, these are obviously coinage metals. There's a reason why they were coinage metals. So the other one obviously is gold, going to gold solid, right? So all of these are metals that lie above just the normal standard hydrogen electrode on that reduction potential table. And so therefore these guys will not be oxidized by just normal everyday acidic solutions, right? They are fairly stable comparatively. Anything that is below hydrogen on this table will be oxidized and therefore will dissolve in the acid. Now, one little last thing to note about that is that when we write this standard hydrogen electrode, these are for metals that are like HCl and HI, right? These are just basic acidic solutions. There is a special case, right, which is nitric acid. So nitric acid, if you guys remember, this is a strong acid, but instead of there being a reduction of just the protons in nitric acid, there's actually a specific half reaction that nitric acid can undergo. So instead of reducing protons in nitric acid, we can reduce the nitrogen from nitrate to nitric oxide. This has a much higher reduction potential. So I think if you look on the table, the reduction potential here for this reaction is like 0.96 volts. And I may have to go back because I maybe am wrong on that. So this lies much higher than the just normal standard hydrogen electrode, which again is at 0 volts. So because of that, nitric acid, can dissolve some of these metals that just normal HCl and normal hydriodic, for example, cannot, right? But again, if a metal lies above this guy on that table, it still cannot be dissolved by that acid. Okay, so with that, I want you to answer this question, right? So in this, I want to know which metal can be dissolved in nitric acid, but not in HCl, right? So this would be a non-spontaneous process, just the reduction of H plus to hydrogen gas. But this one, which is this nitrate reduction of 4 protons plus 3 electrons going to make NO plus water, 2 of these guys, this would be a spontaneous process, right? So again, I would look back in that reduction potential table. You're going to find our 0 volts, our standard hydrogen electrode somewhere. You're going to find above it our reduction of nitrate, right, which is like 0.96 volts. What you're looking for is something that is below this but above this, right? That's going to be the spontaneous process where it cannot be dissolved by just normal acids, but it can be dissolved or it can be oxidized by nitric acid. Okay, so go ahead and give that a try and then come back for the answer. Okay, so again, we're trying to predict which of these metals can dissolve in nitric acid, so which of these metals can reduce nitrate, but cannot dissolve in just normal HCl, so normal just acid. So again, what we're looking for is, again, this position in this standard reduction potential table, right? And so if we started with iron, we want to, again, selectively oxidize solid iron. If we look at the potential of iron, just solid iron on the table, we'll find that iron, again, going long-term to FeS, right? So there's a couple of different iron 2+, iron 3+, but all of them, so we'll just say Fe2+ plus 2 electrons, all of them lie below both the standard hydrogen electrode as well as that nitrate reduction, right? So iron can be oxidized by both HCl as well as HNO3, okay? Now, if we move on to B, if we move on to gold, right? So gold ends up being way up here. So this is our Au3 plus 3 electrons going to Au solid. Again, you're looking for the reduction product being that solid metal. Because because gold is above both nitric acid as well as HCl in that table, then gold cannot be dissolved by anybody, right? That's why gold is, as valuable as it is, it's not dissolvable in an acid. And so gold cannot be dissolved by either. So this guy can be dissolved by both. This is neither. And then finally we get to silver, and where we find silver, and again, this is the silver going to solid silver, is right in between the nitric acid couple and the just normal standard hydrogen electrode couple, right? So it is below this guy, so it can be oxidized by nitric acid, but it's above just normal HCl, so that is not a spontaneous process. It cannot be oxidized by just standard HCl. So the answer here is silver, and again, it's just based on the position in that standard reduction potential table. Okay, so again, with respect to the acids, it's a nice little just spin-off of being able to predict a spontaneous redox process just by looking at reduction potentials and just by looking at positions in that table. Acids, and we're going to move on to the relationship between cell potential, which is what we've been talking about, Gibbs free energy, and the equilibrium constant. Okay, so we have talked about Gibbs free energy, right? What is Gibbs free energy? What does it tell us about a chemical reaction? Whether or not something is spontaneous or not. So if we have a spontaneous reaction, what is the sign for delta G? It's negative, right? Now, with respect to our new little cell potential, for a spontaneous process, what is the sign for the cell potential? Positive, right? So obviously there's a relationship here. One tells us the overall spontaneity of a redox process, where the other tells us the spontaneity of any type of reaction. We could spend time deriving that actual relationship, but I'm not going to do that. I'm just actually going to give it to you, okay? So the relationship between Gibbs free energy, which is what we've talked about, and the cell potential is delta G is equal to minus NF times the cell potential. There's a couple of new things that we're introducing here. The most important one is this guy, F. This is a constant. It is Faraday's constant, and it is 96485. And the units here are coulombs per mole. And this is per mole of electrons. Again, the cell potential is what we've been calculating. You'd get that from our standard tabulated list. What do you think N stands for? It's probably number of moles, but what do you think is number of moles of? Electrons, right? This is going to be the number of electrons that are transferred in a process. So this is number of moles of electrons. So as a note here, just with respect to units, because that's going to be mildly important. So when we take this together, when we have N, which is number of moles of electrons, and we times it by F, F has units of coulombs per mole of electrons, and then we times it by the cell potential. What are volts? What were they because cell potential is measured in units of volts. But what was a volt? It's a joule per coulomb, right? So we end up here in joule per coulomb. So the moles of electrons cancel, the coulombs cancel, and so when we calculate delta G for any of these processes, we're going to be ending up in units of joules, okay? And so ideally, you would then convert to kilojoules after that. Okay, so also, what's nice and handy is we have this little negative in front, right? So this negative, if the cell potential is positive, that negative is going to make delta G negative overall, and vice versa, okay? Okay, so let's go ahead and utilize that. Let's say that we have a reaction where all they give you is the electrode potentials, the reduction potentials for a couple of different half reactions, and they want you to calculate delta G, right? So that would be a very strong hint if you're not given delta H, if you're not given delta S or delta GF, that you're going to have to utilize this relationship. Delta G is equal to minus NF E cell to calculate delta G, okay? And again, everything for right now is at standard state. Okay, so we have a chemical reaction. We've got iodine reacting with bromide to make iodide and bromine. Who is being oxidized in this reaction? So we've got iodine. This is the elemental form of iodine, so this has a oxidation state of 0. What is it going to on the product side? A -1, okay? So if I was going to write, this is oxidation or reduction? This is a reduction, so I'm going to write the reduction half reaction. So if I have an I2 and it goes to make 2 I minuses, for each I am gaining 1 electron. So how many total electrons do I have to gain if I have 2 I's? 2 electrons, right? So for this reaction, for this half reaction, it's I2 plus 2 electrons going to 2 I minus. Then on the other hand, for bromine, we have a -1 here, and we have a 0 over here. So bromide, is being oxidized. Oxidation. So we've got 2 Br minus going to make a Br2. And again, same type of concept. Each B is losing an electron. There are 2 Bs overall. So we're losing 2 electrons. So now all I have to do is go look at my little tabulated list, my little standard reduction potential table, and look up the reduction potential for both of these half reactions. So when I do that, I come back, zoom in, I get a reduction potential for the iodine of a positive 0.54 volts. And same thing for the bromine, I get a positive 1.09 volts. And again, those are just coming from me looking those values up in the table. Okay, so again, purpose of this is calculating delta G, but we're going to have to do that through calculating the cell potential. I now have my 2 half reactions and their standard reduction potentials. I'm going to utilize that to calculate the cell potential. So this is the potential of the cathode minus the anode. Who is the cathode here? Cathode is reduction. Who gets reduced? The iodine. So we've got a positive 0.54 volts minus the oxidation half reaction, a positive 1.09 volts. This gives us overall a negative 0.55 volts. So just as is right now, is this spontaneous? So what would you predict the sign of delta G would be? Positive, right? So hopefully it'll end up that way, or something terribly wrong has gone on. All right, so now that we have that, we are ready to calculate delta G. So we have a minus in front, that's important. What is N here? This is kind of the only tricky one. Yeah, it's the number of moles of electrons transferred, but it's the number of moles in the balanced redox process. So for this, it's 2, right? Because 2 is what balanced the charge. So we have 2 electrons times Faraday's constants, 96485, times the cell potential, minus 0.55 volts. So when we multiply all that together, we get a positive 100,006 or 106, well, no, yes, 1,133 joules, which we convert to positive 106 kilojoules. Okay, so 2 steps. You've got the actual reaction, you need to figure out the cell potential, and then utilize that to figure out delta G. Okay, so let's go ahead, we'll try that. This is a little bit hard. So I've got sodium reacting with water, forming hydrogen, hydroxide, and sodium +1 ions. I want you to calculate delta G for this reaction. People having trouble finding the half reactions? No? Okay. They're there, or at least one of them. Okay, so let's talk about this one because we do need to get to the end of this stuff. So some of the problems with this one that you may encounter, it's hard to find that reduction half reaction, the water going to hydroxide and hydrogen. It's on there, but you have to look for it. So in this one, we have sodium being oxidized, right? We go from a 0 oxidation state to a +1. So our oxidation half reaction is Na solid going to sodium +1 electron. That's what you're going to find in the table. Why do they multiply it by 2 in the overall balance reaction? Why is there a 2 in front of the sodiums? Well, we'll get to that. Hold on. We'll get to that actually. Maybe the reduction will help that out. So for the reduction half reaction, this is 2 H2Os plus 2 electrons going to make H2 plus OH minus. Right? So, again, if we were going to combine these 2 half reactions to balance it, what would I need to multiply my oxidation half reaction by? 2, right? Because, again, if we want to balance with respect to charge, these guys have to be equal. So when we sum this up, they multiply the oxidation by 2 to get 2 total electrons on the oxidation half reaction, right? That's N. It's the balanced number of electrons. We're going to find this guy in the table like this. It's not going to be 2 Na going to 2 Na plus 2 electrons. It's going to be this one, Na going to Na plus 1 electron. But again, when they sum these guys together, they had to multiply this thing by 2 to get 2 total electrons overall. That's what cancels, and that's what goes in for N down here. Okay? All right, so then when we go to the table, even though they did multiply that by 2, we don't have to do that when we talk about the potential. We leave that alone entirely. So I'm just going to write down 2.71 volts. That's what you'll find the sodium half reaction to be. For this water half reaction, it is a minus 0.83 volts. So the reduction half reaction is the water. This is a minus 0.83 volts. Minus a minus 2.71 volts. That gives me a positive overall 1.88 volts. So now when I plug it into my little equation, I'm going to get a minus 2 electrons times Faraday's constant times my cell potential, delta G overall. So delta G naught is equal to a minus 362.8 kilojoules. And I've taken the liberty of converting this. Okay? Okay, so next. I know it's fast. I am recording this at this point in time, so we can go back and watch this afterwards. A couple more things we have to derive, okay? The next one is the relationship between the cell potential and the equilibrium constant. So again, this is going to come back from the relationship that we just derived, which was delta G is equal to minus NF E cell. It's also going to come from delta G is equal to minus RT ln of K. We got this from the thermodynamics chapter. So we spent some time deriving this guy. Again, we're trying to form a relationship between this and this, okay? So all I'm going to do is I'm going to substitute this in for delta G. So that's going to leave me with minus NF E cell is equal to minus RT ln of K. Again, K is just the equilibrium constant. I'm going to divide both sides by minus NF here. Divide both sides by minus NF. And I'm going to be left with E cell potential, is equal to RT over NF ln of K. So this is our nice little handy relationship between the cell potential and the equilibrium constant for that overall reaction. Now, there's a little special trick because most of the time this occurs at 25 degrees Celsius. So R is always the same. This is usually 298. This is always Faraday's constant. The only thing that varies here is N, if we are doing this at 25 degrees Celsius. So this can also be written as E cell is equal to a 0.0592 volts over N times log base 10 of K. Both of these are equivalent, right? They just essentially translate into one another. This is specifically at 25 degrees Celsius, whereas this relationship is at any temperature. And I tend to prefer to like this relationship better because, again, it's not that hard to remember, but this is a little bit easier to remember overall. It's up to you. That we get it. Okay, so I'm going to go ahead and do this example. I skipped it in class, and I wanted to go back and go through it. So in this type of problem, we're going to be using our standard reduction potentials, our standard tabulated electrode potentials to calculate the equilibrium constant for whatever reaction they're presenting us with, right? So again, we're looking for K, right? And there's lots of different ways to determine K. There's delta G, right? We have a relationship for delta G and K. There's also just the concentrations of everything in K. In this type of problem, what they'll be giving you are these tabulated potentials, these reduction potentials, and they'll be asking for K. So you'll know at that point in time, the only way to go from this to this is the equation that we just derived, okay? So in that equation, we had delta, not delta, I always get delta, E naught, so cell potential, E naught cell is equal to RT over NF, and this is ln of K, okay? So we're looking for this guy, we're looking for K, and we're going to utilize our little cell potential that we're going to calculate from our standard reduction potentials to determine what K is. So first thing to do is figure out what this guy is, and to do that, we need to look at our reaction and figure out what's been oxidized, what's been reduced. So for this problem, we've got copper in the zero oxidation state, the elemental form. It goes to copper 2+, so this is our oxidation, right? So we can write our oxidation half reaction. Down here, we've got copper solid going to copper 2+ plus 2 electrons. And then we can write our reduction and write it correctly. Our reduction half reaction. So what's being reduced here, we have a +1 for hydrogen. It's going to a 0. So for the balanced one for this guy, we've got 2 hydrogens plus 2 electrons going to H2. Because again, we have one hydrogen going from a +1 to a 0, but 2 hydrogens overall because, again, it's got 2 hydrogens here. So because of that, we get 2 electrons for this balanced half reaction. All right, so now we'll go to our nice little table. We'll look up these standard reduction potentials. So our standard reduction potentials for these guys, the copper is a positive 0.34 volts, and the protons, the hydrogen, is our standard hydrogen electrode. This is just 0 volts. Okay, so now we'll utilize that to calculate the cell potential at standard state. This is the potential of the reduction half reaction of the cathode, which is 0, minus the potential of the oxidation half reaction, the anode. So this is 0.34. That gives us overall a minus 0.34 volts. So already you should note that this is non-spontaneous in the forward direction. Okay, all right, so now what's next? Well, for the remainder of this guy, we need a couple other things. So right now we have E cell. I'm going to go ahead and take this equation and plug it in. Minus 0.34 volts is equal to R is gas constant, 8.314. T is temperature. We're at 25 degrees C, so this is 298 Kelvin. Over N. N is the number of moles of electrons transferred in this balanced redox process. So we've got a 2 and a 2 whenever these were combined. So this is 2 moles of electrons, and then 96485, Faraday's constant, and then ln of K. So when I solve for this, I'm going to move everything in front of ln of K over to the left side. So I'm going to multiply by 2, multiply by 96485, and then divide by R and T. That's going to give me a minus 26.48 is equal to ln of K. And then to solve for K, it's just E raised to both sides. So K ends up being a very small number, 3.2 times 10 to the minus 12. Okay, and so again, this makes sense. We've already known that this is a non-spontaneous redox process in the forward direction, which means that the reverse reaction is spontaneous, right? So for a very tiny equilibrium constant, that means that reactants are present in much greater abundance at equilibrium, and that again correlates with the non-spontaneous in the forward direction, spontaneous in the reverse, right? So they're going to the reactants, they're making more reactants because, again, they're trying to get to this nice tiny equilibrium constant. And then, okay, so now I'm going to go ahead and do this question as well. So this is a little bit harder, and I'm going to go through it, try to explain what makes it a little bit harder. But again, it's the same type of problem. We're looking to calculate the equilibrium constant given that you're going to be given these reduction potentials or these electrode potentials for the various half reactions that make up this overall redox reaction. Okay, so same exact thing as we did before. First thing we need to note is who's been oxidized, who's been reduced. What is our oxidation half reaction? What is our reduction half reaction? So in this problem, we've got iron going from a 0 oxidation state to a positive 3. So this guy is being oxidized, and most importantly by losing 3 electrons, so minus 3 electrons. And then we've got protons going from a +1 to a 0 over here. So we'll go ahead and write that out. We've got our oxidation. So this guy is Fe solid. It's being oxidized and going to Fe3+, and again, it's losing 3 electrons. And so for reduction, again, we're looking at just the single couple, what we're going to find in the table. What we're going to find in the table is 2 protons plus 2 electrons going to make H2. All right, and again, this is our standard hydrogen electrode. The only reason why they have balanced these guys, why they have different numbers up here, and up here is because when they've added them together to balance the overall redox process, they had to have the same numbers of electrons. When they're written just in their normal half reactions, it's a 3 and a 2. So to balance these overall, so they have the same number of electrons, they would have to multiply this guy by 2 and this guy by 3. We don't do that though. We do that whenever we try to balance the reaction, but for calculating the overall cell potential, that does not concern us. And I know it's kind of harsh because it's like all these things that you've learned. When you multiply something by a number, you need to multiply the other thing by a number, but just ignore that for electrochemistry. Okay, so then all we have to do is go into our table and find these half reactions, right? So we have iron going to iron 3 plus 3 electrons. What we'll find in the table is Fe3 plus 3 electrons going to make Fe solid. That has a reduction potential of a minus 0.036 volts. And then in our table, protons gaining electrons going to hydrogen. That is our standard hydrogen electrode. So it has a potential of 0 volts. So now we'll calculate the cell potential from these guys. So this is just going to be our reduction, our cathode, which is a 0, minus our oxidation, our anode, minus a minus 0.036 volts. So this gives us a positive 0.036 volts. Notice that's not very large, right? So comparatively, we've been calculating voltages that were like 1.8, 2.7, etc. This is a very small potential difference, but you'll see it actually generates quite a large, even at this small of a value, it generates quite a large equilibrium constant. Okay, so now that we have that, we can plug that in is equal to RT over NF ln of K. So go ahead and plug in our values. We've got a positive 0.036 volts is equal to 8.314,298 all over N here is, now this is the trick, right? So N has been this number of electrons transferred, but again, that's for the overall balance reaction, right? So when they balance this, they multiplied this guy again by 2 and this guy again by 3 to make the total number of electrons transferred for both processes 6 overall to add them. So N here is 6. It's for the balanced overall redox process. And again, it has to take into account the balancing of the charge. Okay, so this is 6 electrons. And then we've got Faraday's constant 96485 ln of K. So we're going to manipulate some things. I think, yeah, I counted for 6. So when I multiply by 6, I multiply by 96485, divide by 8.314, divide by 298. I get 8.4 is equal to ln of K. Oh, it's like a dividing sign. And so then to solve for this, E raised to both sides will give me K. So K is equal to 4.5 times 10 to the 3. Right, so it's actually fairly large, even though, again, we had a fairly small overall cell potential. Okay, so hopefully that helped. We have time at the end. So go ahead and try this question. So this is just a nice kind of give me multiple choice type question. You'll see things very similar to this, kind of like this overall understanding between K and delta G and E. So in this problem, we have a redox reaction that has a equilibrium constant of 1.2 times 10 to the 3. I want to know which statement is true regarding the sign of delta G and then the sign of the cell potential. So go ahead and try that, come back, you can pause the video. Okay, so the correct answer here is E cell is positive and delta G is negative. So the correct answer is C. So again, K greater than 1 means that products are favored. Products are favored at equilibrium. meaning that if we're starting at standard state, which is usually what we're doing when we've got this guy involved, starting at standard state, we're at 1 and 1, and if equilibrium constant is greater, then the forward reaction is spontaneous, right? Products are favored, forward reaction is spontaneous. So forward reaction is spontaneous, so then delta G is negative, and E, and again, these are delta G naught, E naught is positive. Both of these give us an overall spontaneous forward reaction. On the other hand, if it was non-spontaneous, then delta G would be positive, and E would be negative, and more importantly, K would be less than 1. Reactants would be favored at equilibrium, so the tendency with starting at standard state would be to go to the left. Left is spontaneous, meaning the reverse of these guys is spontaneous. So this guy's forward is non-spontaneous. Okay, so hopefully that makes some sense. Okay, so I completely just overwrote everything I'd recorded on this slide. So I'm just going to say this really quickly to try to reiterate what I was trying to say in class. So thus far, everything that we've been dealing with cell potential has been at standard state, right? And so standard state, we've got concentrations of 1 molar for anything that is an aqueous ion. And then for the solids, everything that we've been dealing with there, it's been just the pure solid. Also, if there's been a gas, it's been at 1 atm, okay? So all of these cell potentials that we've been measuring have been at 1 molar concentration of everything. And again, we've been measuring overall the standard cell potential, E naught, okay? So now the big question is, well, what happens if we move away from non-standard conditions, right? So what happens if concentrations change? How is that going to affect the overall potential that is generated between our two half cells? So now we're going to want to calculate E, right? This is just E cell. This is the cell potential at not standard state, or maybe I should say that better. The cell potential not at standard state conditions, right? So these are going to be conditions anything other than 1 molar. Okay, so how are we going to go about doing that? Well, it's going to involve something very similar to what we did for delta G, right? To the exact same thing. We're going to derive our relationship from that exact same equation, delta G is equal to delta G naught plus RT ln of Q, knowing that delta G is equal to minus NF E not at standard state, and delta G at standard state is equal to minus NF E at standard state. So I can substitute both of those in. We've got minus NF E cell is equal to minus NF E naught cell plus RT ln of Q. We can do the exact same thing, divide both sides by minus NF, and then this guy by minus NF. And what we're left with is something called the Nernst equation. So this is the cell potential, not at standard state, is equal to the cell potential at standard state minus RT over NF ln of Q, where R and T and F and N, they're all their usual suspects, right? Same things that we've been dealing with thus far. Okay, so how would we utilize this, right? How would we determine the cell potential once we've moved away from standard state, given that we have, again, that nice little standard tabulated list of cell potentials at our disposal? So let's say we have a reaction. We have this 10 2 plus manganese going to 10 solid manganese 2 plus, and we want to calculate two different things. We want to calculate the cell potential, so E naught cell under standard conditions, and then we want to calculate it when we've moved away from standard conditions, when the 10 concentration is 0.01 and the manganese concentration is 2. Okay, so to do that, again, what do we probably have to do for A? Just calculating the cell potential at standard state. What do we need to do? Write the half reactions, right? We have to look up the reduction potentials for the two half reactions. So who is being reduced here? So we've got reduction is who? 10, 2 plus, SN 2 plus. How many electrons does it gain? 2 electrons goes to make 10 solid. And then the oxidation, who is that? We've got manganese, solid, going to Mn 2 plus 2 electrons. So same exact thing. We go to our little tabulated list. We find that 10 has a reduction potential equal to a minus 0.14 volts. And manganese has a reduction potential equal to minus 1.18 volts. So we plug that into our normal little cell potential equation. So potential of the cathode, which is minus 0.14 volts, minus a minus 1.18 volt, gives me a positive, overall, positive 1.04 volts. Okay, so that's A. Standard state, B. Moving away from standard state. So to do this, if we want to calculate this guy, not at standard state, we need the cell potential at standard state, minus RT over NF ln of Q. How would I calculate Q for this reaction? So concentration of products over reactants raised to their stoichiometric coefficients. So if I wrote Q up here, and go ahead and I'm going to write the concentrations of these guys down below just to remind myself. 0, 1, 0, 0. What would Q be? Do I include the 10? No, right? Because it's a solid, so we ignore this. So right now it's only the concentration of Mn raised to the 1, because it's got a 1 in front of it, over the concentration of Sn raised to the 1. Again, we ignore this guy because it's a solid, and they don't get included in the constant, or the equilibrium constant expression. So when we do that, we've got 2 molar divided by 0.01 molar. Overall, that gives me a Q. What is it? 200. Q is equal to 200. Okay, so now that we have that, we already know the standard state cell potential. So this was a positive 0.04 volts. Now, R, standard normal R, 8.314. T, what temperature are we at? I forgot. 298? Or yeah, 25 degrees Celsius, so 298 Kelvin. What is N? Number of moles of electrons. What is it particularly for this guy? 2, right? So this is going to be 2 times 96485. Faraday's constant, ln of 200. When I multiply this guy together, I end up getting a positive 1.04 minus, I don't even know what happens there. So when everything happens, we come back, everyone's super excited. It ends up being a 0.97 volts. Okay, so just conceptually, I want to make sure this makes sense, right? At standard state, right? Standard state, what were the concentrations of this guy and this guy? 1, right? So they were 1 molar, and they were 1 molar, right? And that had a potential of 1.04 volts. So it was nice and spontaneous, okay? What have we done to disrupt that standard state condition? When we move to the conditions in B, what has that done comparatively to the 1 and 1? We have increased the concentration of a product of our cathode, right? And we have decreased the concentration of a reactant of our anode. If we go back to the Chatelier's principle, right? If we increase this guy and we decrease this guy, what is it going to want to do? Increase products, decrease reactants. What is it going to want to shift to? A little bit back towards the left, right? So how does that translate overall with respect to what happens to the cell potential? It's still spontaneous. It's still a spontaneous process, but it's a little bit less spontaneous, right? Because again, it was spontaneous with 1 and 1, nice and big. We've increased a product, we've decreased a reactant. It wants to shift a little bit back to the left, right? So now it's a little bit less spontaneous. That's why we see this overall decrease with respect to the reduction potential between the two half cells. We're pushing essentially the electrons kind of a little bit back to the anode. Okay, so I'm amending this right now with one final thing on these non-standard state voltaic cells that you guys are going to be dealing with. So if you remember, back on Tuesday, we talked about the shorthand notation with respect to these voltaic cells, right? So in that shorthand notation, we always put the anode half cell on the left, and it was separated via salt bridge to the cathode compartment, the cathode half cell on the right. And how we usually wrote that was electrode, so specifically what is the metal, followed by a single line to denote a phase change, followed by the electrolyte, so whatever that metal was sitting in, and this is usually its overall ion partner. Again, a double little bar here denotes a salt bridge. Then this is going to be followed by the electrolyte of the cathode, electrolyte, phase change to the electrode of the cathode. Okay, so for this specific reaction, this voltaic cell that is created in this specific reaction, the anode is given by what's happening with manganese. It's our oxidation half cell. So we would write that shorthand notation as Mn, and then we write solid, and then single bar phase change to the electrolyte, or the ions that manganese solid is sitting in, which is Mn2+. We'd write aqueous after that. There's nothing else in there, it's just manganese by itself. So then we have double bar for the salt bridge. Now the electrolyte for the cathode half cell is our tin, so we would write Sn2+, aqueous, solid line indicating a phase change to Sn solid. Okay, now this is our shorthand notation to essentially depict this exact same thing. And there's nothing really different or anything weird about that. The only thing I wanted to mention about this is sometimes they'll use this shorthand notation when, again, they're trying to denote things not at standard state. So for example, in B, we've moved our concentrations of our tin and our manganese away from standard state. So the way they would depict that in the shorthand notation is it would be the same thing. So the electrode at the anode, the metal at the anode, which is Mn, solid, phase change, same electrolyte, Mn2+, but now they would write its phase separated by a comma and then its concentration. They typically will do this to denote that we're not at standard state and we've moved away with respect to the concentrations in solution. So then the concentration of manganese in B is 2.0 molar. And again, all that's trying to tell you is that this electrolyte, this is its concentration. Again, we'd have a salt bridge, we'd have an electrolyte, so 10, 2+, again, aqueous, comma, its concentration, which for this problem is 0.010 molar, phase change to Sn2+, or Sn solid, pardon me, right? So the shorthand for B would be given like this. And again, it's just a way that they're telling you, hey, we've moved away from standard state. These are the actual concentrations of the electrolytes that are in our anode and our cathode compartments, respectively. One more. It's the same thing. We've moved away from standard state. We have a cell, a voltaic cell, that at the anode, at the oxidation half reaction, we have this nickel going to nickel 2+, and then at the reduction half cell, we have this process occurring. they particularly tell you the concentrations of everything in species, right? So this is not at standard state. You're going to be calculating this guy, but to do that, you're going to need to know the cell potential at standard state. So first, I would get this, and then I would come back to this at the end. So go ahead and try that. And if you get an answer, plug it into Socrative. And I will help out, I will give you the reduction potentials for the two half reactions. So one thing I want to help out on really quick before you guys go through this, these aren't balanced the way they are, right? They're just showing you the half reactions. If we combine this to form this overall redox reaction, this guy only has one electron being transferred where this has two, right? So if I wanted to balance with respect to charge, what do I need to multiply that reduction half reaction by? 2, right? So that gives me 2 things overall. So this guy plus 4 protons plus 2 electrons goes to make 2 VO2 plus 2 H2O. So then I would combine that with the nickel 2 plus 2 electrons. This would be the overall reaction that Q would be based off of, which is 2 VO2 plus 4 protons plus nickel solid, going to make nickel 2 plus 2 VO2 pluses plus 2 H2Os, and water is a liquid. Okay, so Q would be coming from this. Okay, so for those of you guys who stayed, did you get the cell's potential at standard state? So So standard state cell potential, E naught, that was the cathode minus the anode. So we had 1 volt minus a minus 0.23 volts. So they gave us a positive 1.23 overall. Are we good there? Okay, so now all we need is Q. And again, Q comes from the balanced overall redox reaction. So that's the big trick in this one, is that you do have to have this to be able to determine Q exactly, right? So we wrote out the Q expression. We've got concentration of products. So we have nickel. We've got VO2+. Again, that's raised to the 2 because it's raised to the stoichiometric coefficient. We've got VO2+ on bottom, raised to the 2 because of this guy. And then protons raised to the 4th power. We don't include nickel, and we don't include water because, again, they don't change their form. Solid, liquid, or liquid, solids, we don't include in the constants. Expressions. I can't talk today. It's all right. Okay, so then once we have that written, now we can go ahead and plug in our values for Q. So we've got 2 for nickel. We've got 2 for VO, but that's squared. Now this is over VO2, which is 0.01. That's squared. And then 1 for protons, which is raised to the 4th power. So when you guys multiply all of that together, you get 80,000. So 80,000 is what Q is. So now we'll go ahead and take that to our Nernst equation. So we've got cell potential, which was our positive 1.23 volts, minus R, 8.314, T, which is 298, over N. N is the number of moles of electrons. And again, that was up here. So this is 2. And then 96485. And then ln of 80,000. Did I do that? No, I just put my calculator and then I don't even write the answer. So we take the natural log of 80,000. You multiply all of this together. It ends up being a positive 1.09 volts. And I may have rounded weird there. I think in the actual answer, I wanted 4 sig figs. This was 8.5 volts.